Yesterday, we had kind of an awkward moment that you were not aware of, but I was. I assigned you an assignment where I thought that they gave you the graphs of f, only in your assignment they were f prime. So, what I need to do for you is to teach you something. And what you guys need to do right now is to point at me without laughing and say, "You stupid teacher." Okay, hold on. There was a lot of smiling in there. Can somebody do it being fully serious? Scott Grabowski by far had the best during second hour. Okay, Taylor, go ahead. That was pretty good. Very good. Yes.
You ungrateful idiot of a teacher.
I like it. I like it. I like it. So I need those kind of things to be able to recover from, the depths of the idiocracy that I display. Okay. Yeah. Yes. I know. I know. I know. I probably ruined your day. Okay, here we go. So, uh, the beginning numbers like 5, 6, 7, 8. So, what I want to show you is this. Okay, if you did them, you don't have to go back and redo them. But what I do need you to do is to ensure you're learning. So make sure that you understand what we do right now. I will give you one to practice, and then when you get the study guide for the test, you'll also be able to look at that. If you want to go back and redo them, go ahead, but you do not have to. They would be pretty easy to do once you see it. So here I give you F. For the others, I give you F prime. Now, when you look at this graph right here, it's pretty easy to see the intervals of increasing. Where is it increasing? From negative infinity to negative 5, and then union with what? Negative 2 to infinity. Where is it decreasing? Very good. Concavity, approximately where do you see the point of inflection occurs? Approximately. Negative 3, 0. So that would mean that I'm concave down from and concave up from 3 to infinity. Whoop. Do I have a local max? Where does it occur? Negative 5 and positive 2. And the local min? Yes. And negative 2, negative 2. Okay, so easy to look at a graph and be able to identify those. But really, our inflection is, really an estimation, which is, okay in this situation. But now we want to look at f prime. And I really encourage you to make your number lines. When I did my master's paper a couple of years ago, 80 pages of writing, 90 pages of writing, and then another 60 or 70 pages of appendices. One of the graphic organizers that were found to be very helpful was this basic number line. For students who did not make the number lines, they performed significantly lower than students who did make the number line. So I encourage you to do so. The top number line is f prime. The bottom is f double prime. Now, remember, when we labeled f prime of x, okay, when we labeled it, we would label on the number line the critical points. That means where the derivative is equal to 0 or where it's undefined. There's nowhere in this graph where the derivative is undefined, but we'll see, and this is the key for the day. Think about it for a second, and then I'll ask you to answer when I ask you a second time. So just think about it. Don't shout out an answer. Where is, on this graph, f prime? Where is f prime equal to 0? Okay, now I'll allow you to answer. Where is f prime equal to 0? A lot of people might say positive 1. That's not the case. The derivative of f prime, which is f double prime, is equal to 0 at that spot. But if this is the graph of f prime, I'm simply asking where is it equal to 0? It is equal to 0 at -3 and 5. So I'm going to mark -3 and I'm going to mark +5. This is f prime. This is f prime. These two graphs have no relation back and forth. I'm making a new one. Yep. So look at this. This is tricky. Right here. Okay, so I'm going to look to this side of -3. Is f prime positive or negative? Why is f prime positive? Because it's sitting above the x-axis. This graph is positive. It sits above the x-axis. Between -3 and 5, the graph sits, so f prime is negative. And then after 5, the graph is above the x-axis, so it is. Now, raise your hand if you're semi-confused about that. It's okay. Okay, only like half a hand went up. Should be more. But this is generally where it starts to then make sense for people. When we look at f double prime. F double prime is the derivative of the derivative, correct? So I want to find where the second derivative is equal to 0. That's where the derivative of this graph is equal to 0. At what spot is the derivative of this graph equal to 0? 1. Tangent line is equal to 0 at that point. Now, I'll draw a few of these out for you. F double prime, again, is the derivative of f prime. What things do we draw to show the derivative of a graph? Draw tangent lines. So when I draw tangent lines, that represents the derivative of this graph. The derivative of f prime is f double prime. So you tell me, as I draw these right now, are those derivatives positive or negative? They are negative. They are going down. So therefore, from 1 on back, the second derivative is negative. As I draw tangent lines on here, are they positive or negative? Positive. So after 1, the second derivative is positive. She's so loud. All right, so increasing, okay. Does the first derivative or the second derivative tell us about increasing? The first derivative. It's increasing where the first derivative is positive. So therefore, it's increasing from union with. It is decreasing from concavity. First derivative or second derivative? Second derivative. Concave down where it's negative. So from -infinity to +1, and then concave up from 1 to infinity. Local max occurs when the first derivative is equal to 0 and it changes from increasing to decreasing. Where is the first derivative equal to 0 and changes from increasing to decreasing? -3. Now, if you want to come up with the y value, are you able to? No, we don't know the position of the original function. We have nothing to plug it into. We have no idea. So you're absolutely right. The original, this graph, f prime, has a local min. It does not have a local max. F prime has a local min. We're not asking about f prime. We're wondering about the original function. If I were to graph the original function, Taylor-Willis, it would look something like this. So see how this f prime is equal to 0 here? Local max. See how f prime is equal to 0 here? Local min. See how the derivative of the derivative is equal to 0 here? Inflection point. It's not easy to think these things through. That's why you're best to go back to the number line test and just do what it says. Where's the local minimum going to occur? 5, and we don't know that spot. And the inflection, does the first derivative or second derivative tell us inflection? Second derivative, and that's going to be at 1. And again, we do not know what the y value is. Yes. What's that? Yeah. This one right here. Okay. Again, we're given f prime. I'm going to make my number lines. And these are the type of AP calculus questions that they would have. Okay. They will give you f prime and ask you then to deduce information. I will be honest, whenever I was asked these questions, I never ever made the number line. Because I was generally able to just look at the graph and understand. However, out of 10 questions, I would generally make a mistake once. If I make the number line, I don't ever make a mistake. If I have to teach it, I'm not simply going to just tell you, look at the graph. I'm going to tell you to make these number lines because it makes sense for everybody. Where is f prime of x equal to 0? -5, -1, 3, and 6. Is the first derivative right here? Look at this. This is where a lot of people make a mistake. Is this derivative positive or negative? Positive. Hunter, why? Why? Because it's above the x-axis. This is the first derivative. It sits above, so it is positive. The second derivative is negative at that spot, okay? So positive, negative, positive, negative, positive. It will continue in that way, all right, as we look at it. Second derivative. Where is the second derivative equal to 0? That's where the derivative of the first derivative is 0. So that spot, which is -3, 1, 4. Megan, did you ask a question, or Amber? I thought I heard one. Oh, yeah! All right! Yahoo! All right. So good. Now is the value of the, so here's where people make mistakes. They start asking themselves about increasing, decreasing concavity. Don't ask yourselves about those things until you've done the first and second derivative test. Okay? So, right here. Is the value of the second derivative positive or negative right here? Negative. Then positive, then negative, then positive. So what is my interval for increasing? -infinity, -5, union with. -1 to 3, union with. 6 to infinity. And my interval for decreasing? -5, -1, union with, 3 to 6. Concavity, concave up. -3 to 1. And -4 to infinity. Concave down. Whoop. Concave down. Yes. Because the second derivative is positive between -3 to 1, it is concave up. Yes. Okay, local max. Why? Yes. Good. It goes from increasing to decreasing. Therefore, it is a local max. And positive 3. That's where we have them. We don't know the y values, but we know that x equals -5 and positive 3. That's where we're going to have local maxes. Local mints. -1 and positive 6. The definition of an inflection point is where concavity changes. Does concavity change from positive to negative or negative to positive? Negative to positive, positive to negative, negative to positive. So these are all inflection points. X equals -3, 1, 4. We don't know exactly what the previous graph looks like, but if we want to, we could get a general sketch. What degree equation is this? It's a fourth, so what would the original graph be? A fifth. You know, it might look something like positive, so I'm increasing my rate. So it might look something like this. It might look something like that, okay? I'm not going to ask you to do that. So, anyway, you can see derivatives equal 0 there, local max. Derivative equals 0 there, local min, local max, local min, and your things check out. And also your intervals, concave down, concave up, concave down, concave up. So, you know, but this is that higher level thinking. Before lunch, try next one on your own. I believe in you. I believe you can fly. Okay, I know you can interpret this when we're done. My question is, did you get all the right intervals? I got -8, -4, 0, 4, and 10. Oh, whoop. I messed up the bottom, didn't I? Yeah. So the first derivative, or the derivative of the derivative is positive here, negative, positive, negative, positive, negative, positive, negative, positive. Okay. So, and then you can deduce information from there. So Bo's question is in regard to, if I can quick make just a little drawing here. Suppose I have, say, -2, 1, 1, 2. Okay. So if this is f double prime of x, right? F double prime tells us, you know, we just deduce our number line. So where's f double prime equal to 0? -2, -1, and 2. Is f double prime positive or negative here? It's negative. This is f double prime. F double prime. This is the f double prime. F double prime is negative right here, correct? Positive, negative, positive. So we could tell concave down, concave up, concave down, concave up. Right. So we can tell about inflection points, but we can't tell. Can you tell increasing or decreasing? No, not right now. Okay. Yeah. So the local max are going to be at where we go from increasing to decreasing. So -4, +4. And local min would be -8, 0, and 10. Yep. No. It's such a, yeah. I have had people name their children after me. Inflection are going to be all these listed on the bottom because the concavity changes from positive to negative. If yeah, la 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 la, yeah, right. If you had two positives next to each other, then it wouldn't be inflection because concavity wouldn't change. Okay. All right. So flip your notes over. No, we're not starting something new. You need your calculator. But I'm saying you do need your calculator right now for sure. And what we're going to do is we are now going to take what we've learned about derivatives and that which we've learned in previous math courses, and we're going to put it all together to be able to do some curve sketching, kind of like we did at the end of yesterday. And I think that this is some of the coolest stuff because this amasses a lot of what we've learned throughout our math careers and puts it together for one purpose. So the first thing you want to think about when you curve sketch, and I won't ask you to always do this, but you want to think about domain. Domain is the x values that you can plug into the equation. If it's a rational function, I'm sorry, if it's a polynomial, you can plug anything in. But if I have something like this, 2 over x minus 4, what value can't you plug in? Right, so you would want to understand that that's part of your domain. X can't be 4. And then, if you have the square root of x plus 3, x would have to be greater than or equal to what? -3. You can't plug in a value smaller than -3. So you should always be able to think about domain and understand what kind of inputs you can have, and then for range, what kind of outputs you can have. For example, if you have y equals x squared, the graph looks like a parabola, but it never goes lower than what y value? 0. So therefore, your range is always y is greater than or equal to 0. So you should always be able to think about domain and range. That's something we've done in previous years. Intercepts is a great way to get a sketch of a graph, and that's something that we've talked about in previous courses. So intercepts, to find the y-intercept, you set x equal to 0. And to find the x-intercepts, you set y equal to 0. That way we know where it crosses the axis. And that's appeasing to us because when you get to use the number 0, generally things work out well. Symmetry, we don't really talk about too much. That is something that we talked about pre-calculus, but I don't come across too many times where people in calculus really say, oh yeah, this is symmetrical, so I'll do this. They generally recognize it on their own. Asymptotes, say we have 2 over x minus 5. Where would you have a vertical asymptote? Yeah, you have a vertical asymptote at x equals 5. You also have a horizontal asymptote at y equals 0, which you don't know about yet, but I'll quick tell you why. If you set this limit as x goes to infinity, what's this whole thing going to go to? 0. The y equals tells us our horizontal asymptote. And now, do we know how to do infinite limits? I already taught you that, so that's why we're skipping section 4.4 because we already did it, and we'll revisit it now in 4.5. So we'll put all the pieces together. Intervals of increasing and decreasing. Increasing is where f prime of x is what? Greater than decreasing, f prime of x is less than 0. A local max, as Megan just says, where f prime of x goes from positive to negative, and a local min is where f prime of x goes from negative to positive, and it's also equal to 0. Concavity, what do we use to check concavity? F double prime. And you get the idea. We don't have to write them all down. We'll save some time. We'll go over this example right here. Okay. So, this is a polynomial. Polynomials behave very nicely. Its domain is all real numbers. A cubic looks like this, correct? So its range is also all real numbers, all right? So we don't have to isolate its domain or range anywhere. It doesn't have any asymptotes. It's a nice, smooth curve that doesn't have any disruptions in it. Its intercepts, okay? That's something that we can use and talk about. In order to find the y-intercept, I plug in 0 for x. Plug in 0 for x, and you get 0. To find the x-intercepts, I plug in 0 for the function value for f of x, or y. I get 0 is equal to x to the third minus 2x squared minus 3x. Can I solve that? Factor out a, and then we get x squared minus 2x minus 3. Does that factor? X minus 3, x plus 1. So I have zeros of 0, negative 1, and 3. So I'll be able to plot those points. Note that last year in pre-calculus, that's all you would do, is simply plot those points. Now that you know real math, you can actually find more points in that. We call it our hidden behavior. Because you don't know, does the graph go like this? Or does it go like... You don't know the type of behavior that it has in between. And that's what we can use our first and second derivative tests for. So, f prime of x. What is the first derivative? Does that factor? No, it does not. So therefore, we have to use our quadratic formula. Go ahead and check your calculator. Somebody give me some values. So I'm going to plug in values to do some testing now. It doesn't factor, so I just have to plug it into my actual derivative. I'll plug in negative 1. Negative 1 squared is 1 times 3 is 3. Minus 4 times negative 1 would be plus 4 minus 3. So that gives me a positive or negative value. Positive. So the first derivative is positive there. What's the value between negative 0.54 and 1.87? 0. Plug in 0, you get negative. Plug in a positive 2. Comes out positive. So we're done with our first derivative test. Now, let's do our second derivative test. Second derivative test, 6x minus 4. X is equal to 2/3. 2/3 would fall right about, I'm going to say there, my number line. Let's look to the left. Plug in 0 and you get negative. Plug in 1 and you get positive. So these tests simply tell us concavity as well as inflection and local max and min. So let's label them. Intervals of increasing. Union. Decreasing. Concave up. Concave down. You have a local max. Where? Why? goes from positive to negative, and it's equal to 0 at that spot. How will I find out the y value? Plug it into the original. So go ahead and point what? 0.88. Thank you. Local min, where does that occur? 0.87. Plug that in. Plug negative 6.1. Inflection. Where does inflection occur? 2/3. Because I changed from negative to positive. Plug it in. Yep. The reason why we plug it in the original is we're always looking for position. We know the x position for all this stuff, but the y position we gather from the original. Okay, so now you get to decide, and this is where I get really excited, because I get to sketch a perfect graph. And for those of you who will disagree with my graph and say it's not perfect, boo to you, okay? Because it's awesome. If you look at my intercepts and my x values here, looks like 3 is the furthest over go. So I'm going to make a graph of 4 units. It looks like my y values go all the way down to, say, -6. So I'm going to go all the way up and down to 8. So you do what you want. I'm going to do what I want. I'm going to make mine 4, 2, you see if you can make yours super duper nice. Mine's real pretty so far. I'm going to plot my intercepts. 0, 3, -1. Now I'm going to plot my local max, local min, and inflections. I have a local max of -0.54, 0.88. So about there, halfway between, I'll go up to 0.88, which would be about a little less than a quarter of the way. And then my local min, 1.87, so not quite 2, and down to -6, so. And then I have inflection at 2/3. That would be 1, 2/3, need 2.6. And does my graph start concave up or concave down? Concave down. And does it start by increasing or decreasing? Increasing. So the first part's going to look like that. So Bo's talking smack right now. He thinks this is better than mine. As long as you want to live in opposite world, that's fine. X to the third minus 2x squared minus 3x. And so what I like to do is I like to go to my window. I like to change it so that the y max is 8. The y min is -8. And I have tick marks, it looks like every 4. And then for the x values, the x min is -4, x max is +4. And it looks like I have tick marks every 2. And then I graph it, and I compare the graph to the original, and I say, what's up? I mean, come on. That is awesome. You don't see it. Oh, my. You're right. I did overestimate that a little bit. It was better second hour, believe me. It was. It was. So I built it up too much. Okay. All right. It's like kind of like watching the growl, you know. Okay, real quick, we're not going to do anymore. I just want to show you as we move forward. Tomorrow, we're going to look, so we still want to see a rational function. We want to see one involving trigonometry. So we got a couple difficult ones to get to, but you don't have an assignment tonight. Just finish up your work from yesterday. You do have an assignment tomorrow, and it'll be fairly lengthy. Lengthy. Time to work on Saturday and Sunday, Hunter. Time to work on math Saturday, Sunday. There you go. Oh, thank you. Thank you. Thank you. All right, go show the world you got some smarts.